Okay, so we will start with the lecture 37 on which is a continuation on the stability of ships on waves. In the last lecture, I mentioned to you, I explained to you how we calculate the wave profile on a ship, that is provided you know the ship length, the wavelength, the length of the load, length of the waterline or the length of the load waterline, or we usually assume it to be the length between perpendiculars. There is usually a small difference between the length of the load waterline or length of the waterline and the length of between perpendiculars, because as you know there is some region in the front and the aft where which does not really come between the aft and the forward perpendicular, slight region is left outside. So, in these studies we will assume that we are dealing with the length between perpendiculars, and what we explained in the last class was that the length between perpendiculars is equal to the wavelength of the wave. So, we have a trochoidal wave, we have been dealing with trochoidal waves in this course in this series, because in this wave analysis we are not going to do any sinusoidal wave analysis. These are waves that have a sinusoidal, a sine or a cosine form. We are not dealing with those kinds of waves, we are dealing with the waves that have a trochoidal form. These are waves that are formed due to, now if you have a particle that is on a circle, and if the circle is rolling, if you consider that the circle is rolling under a straight line. So, if you have a straight line and you have a circle here and the circle is rolling under a straight line like this, the trajectory traced out by that particle on the circumference of the circle is what you call as a trochoidal wave. Now, such a trochoidal wave we have already seen how we can calculate the x coordinate of the trochoidal wave at any instant of time, or the y coordinate of the trochoidal wave at any instant of time, not y, z coordinate of the trochoidal wave at any instant of time. So, x and z, once you have this, you can get the wave profile all over the length of the ship between the perpendiculars, between the aft and the forward perpendicular, we have the total wave profile. So, this is how you calculate the wave profile on a ship. So, this is the in the analysis, in the ship stability analysis, one of the first process is to generate a trochoidal wave that will that is formed over the ship. So, that is number 1 you need to do. Now, when you are doing the stability analysis or when you are doing the structural computations, one of the primary factors that you need to do, okay, now you have defined a ship on waves. Now, there is a problem here, that is we have defined that the ship, suppose you have already drawn a lines plan. I hope you remember from the previous, in fact, I believe it is the first lecture. In the first lecture, we have already defined what is known as a lines plan. It is something that is used in any course in naval architecture, any university in the naval doing a course in naval architecture, the student will be expected or he will be required to perform a lines plan class or lines plan laboratory, in which he will be required to draw the entire lines plan. And just as a quick recap, I will mention that a lines plan is usually a figure that has, it is usually a huge drawing that has 3 main sections in it, what we call as the half breadth plan, the shear plan and the body plan. So, 3 views. Half breadth plan, we are talking about the top view of the ship. So, you are looking from the top, what do you see? That is the half breadth plan, and you know that we draw only the half breadth because the ship is exactly symmetrical, the port and starboard side of the ship are same, there is no difference. So, that is number 1, and then we draw the shear plan. Shear plan is when you look at the ship from the front. So, you have the not front, from the, means if the ship is like this, you look like this. So, this is what you call as the shear plan. So, if you look from, this is the front, if you look from here, the front of the ship, you say that it's called, you call it as a body plan, and you should be remembering that in the lines plan you end up with 3 kinds of lines. You call them water lines, buttock lines and stations. Stations are these in the along the longitudinal direction, you will say that these are stations, and in the transverse direction these are buttock lines. In the vertical direction, these are water lines. So, you have these areas are called water plane areas. So, that line which defines the boundary of that water plane area is called as a water line. So, you will have water lines at different heights, and depending on the draft of the ship you will have a different water line. Now, how will the ship react? Now, the first question that we need to ask is how will the ship react if it is subjected to a wavy first of all let us forget the wavy surface. Let us assume that the ship is now on a water line. Its ship is now on a even water line, means it is on a straight water line, a horizontal line, that is there is no wave as such. We have to bring in the concept of waves because this lecture is definitely on waves, but let us do it without waves first. So, this is the shape. Now, what are two important, this is a water line. Now, what are two important points that we can already assume, we can definitely assume in the case of a ship that is subjected to a that is floating like this. First, you know that the Archimedes principle holds good. Archimedes principle says that the weight of the ship should be equal to the upward force, which is called the buoyancy. Now, how do we get the how do we get the weight? Weight is the total weight of the ship, that is the you have the different you have the hull weight, which is the just the weight of the ship with just the hull. So, you have the hull of the ship and you consider the weight of the member that produces the hull, that is called as a hull weight. Then you have the light weight of the ship, which is the hull weight plus the propulsion machinery. So, you have the propeller, your propeller is added at the aft of the ship, you add the propeller and you add the propeller machinery, for example, a diesel engine or a gas turbine, whatever it is, with that propels the ship. So, you add that. Now, the total weight of this machinery plus the propeller will give you the light weight of the ship. Add to it the different consumables and different cargoes. For example, the cargo that if it is a cargo ship, the cargo that it carries or the containers it carries, weight of the personnel, crew, weight of the stationery, weight of fuel, weight of lubricating oil, weight of water, fresh water, ballast water, add everything to it, you will get the what we call as the total weight, the dead weight of the ship. So, you will get the light weight plus dead weight will give you the total weight of the ship. So, displacement of the ship. So, you will get, so initially you have the hull weight, light weight and the displacement, that is adding the dead weight. Now, this will give you the total weight of the ship. Now, what is the first principle? Again the Archimedes principle states that this total weight should be balanced by the buoyancy force. Now, how will you calculate the buoyancy force? As we know that the buoyancy force is always given by rho into del, where del is the underwater volume of the ship. This is the underwater volume of the ship. So, therefore, weight is something that you have to know, means it is a part of the ship. Ship is, suppose we know all the particulars of the ship as such. Our purpose is now to find, now my purpose in describing this is just to find the position of the water line as well as the position of the ship, the final position of the ship, provided we have every hydrostatic data of the ship. Okay. So, right now I am assuming that I have all the hydrostatic data that is required for the ship, that will include the weight of the ship, the distribution of the weight of the ship, distribution of the weight on the ship. What is the importance of getting the distribution of weight on the ship? Its importance is in getting LCG, that is the longitudinal center of gravity. Now, so I have that, and number 3, so I have the weight of the ship, distribution of weights on the ship, and I also have the Bongian curves. I hope you remember now what are meant by the Bongian curves. Bongian curves are a hydrostatic curve or a type of hydrostatic curve, which actually represents it is actually a curve between the draft and the sectional areas. Again, I am assuming you remember what are sectional areas, that is you have the ship like this. If you slice it like in this fashion, these areas are what are called as sectional areas. We are talking about the areas that are underwater, not the areas above the water. So, the area under the water of the ship at some particular draft. So, whatever be the draft, there will be some area under it, this area. So, that much area under the ship. Now, that is called as sectional area. So, the curve between this draft, and the sectional area, this is called as a Bongian curve. So, as the draft increases, the sectional area will increase. So, you have some curve. Now, provided you have the Bongians at different stations, how will you find the volume of the ship? Question 1. So, suppose you have the Bongians at different stations, how will you find the volume of the ship? It is very simple. You integrate the areas, or you Simpsonize the area, you integrate the areas, you will get the volume of the ship. You have the, so integral A dx will give you the volume of the ship between 0 to L. This gives you the total volume of the ship 0 to L. A is the sectional area at each station. So, you write it like this, sigma 0 to L A into delta x, where delta x, we have done all this. So, this will give you the volume of the ship. So, this, that is the del I am talking about here, the underwater volume of the ship. So, the first step to do in a stability analysis of a ship is to make sure that this rho into del, which is the underwater weight, that is the buoyancy force, is equal to the total weight of the ship. Total weight of the ship is got by balancing all the weights on the ship. So, you sum up all the weights, I have already told you the total displacement, you make it equal to rho del. How will you make it equal? Make it equal is when you, what can you change? This is fixed, this you cannot change anyway. So, the only thing you can do is you change rho into del, or del, you change del. How can you change del? Integral A dx, this can be changed if you can change A. Again, how will you change A? That is the sectional area. Sectional area is a function of draft. So, the only way you can change A is by changing the draft. So, by shifting the draft again upwards or downwards, you will end up with a different value of A, the sectional area at that draft, and when you keep, when the A changes, you will get a different volume, and you keep shifting the draft forward, you keep shifting the draft upward or downward, such that the final weight of the ship is equal to the volume of the ship. So, that is the first step that is to be followed in the stability when you are doing such an analysis on a ship. So, that will give you the draft of the ship on which the ship is floating, means that will give you a stable condition of the ship in which the ship is floating. Now, you have balanced the weights, the forces, you have balanced the forces. Is that enough for complete stability? No, because for a complete stability of a ship, you have to balance the forces as well as the moments. So, if there is a moment acting, the ship, of course, it is balanced as far as the translation is concerned, but the ship will rotate about some point. Which point does it rotate? We have already discussed so much about it. We have talked about trimming. Trimming, again remember, we are talking about the longitudinal movement. So, we are talking about trimming here. We have already seen that the ship always trims about its longitudinal center of flotation, which is known as the water plane, which is known as the centroid of the water plane area. So, that is what you call as the longitudinal center of flotation. A ship always trims about that LCF point. Now, why does it trim? A ship trims because if you have, you know that, let us consider this to be the ship and this to be the G of the ship. Now, you know that at G of the ship, the weight of the ship will be acting. Let us assume that this is B. At B, there will be a buoyancy force acting del, and I will write it as F. The buoyancy force acting, which will also be equal to delta, because it is in a, we have already made them equal, that is the buoyancy force and the weight of the ship has been made equal by shifting the draft. By moving the draft up or down, we have said that the ship is stable as far as forces are concerned. So, in the vertical direction, the sum of the forces is 0. So, it is stable, there is no translation as such. If there is a unbalance of forces, it will translate such that finally it becomes 0. So, the next step is that we are seeing that if G and B occur like this, G is here and B is here, let us assume this distance is LCG, and this distance between becomes LCB. So, at buoyancy this, so this delta acts down, this delta acts up, and therefore, there is a moment, you see there is a moment acting like this. This is a moment that tends to rotate the ship. Now, therefore, if it is like this, if G is here, there is a moment that tends to rotate the ship like this. If G is forward of B, then there is a moment tending to rotate the ship like this. It is because of this two forces acting not on a straight line. If the two forces, there is the force of weight, the weight force acting at the center of gravity, and the buoyancy force acting at the center of buoyancy, if they are not at the same vertical line or not at the same point, then you will have a trimming moment, you will have a moment that causes the ship to trim. Okay. Now, how can we balance it? Now, suppose that the ship trims, you know that as a result of the ship's trimming, B will shift, G does not shift, because G is dependent upon the weights on the ship. It has nothing to do with the whether a ship trims or not. If the weights on the ship do not move, then there is no change in G, LCG, the center of gravity of the ship does not change. But if the ship trims, what will happen? Let us say that the ship trims by forward, the front part of the ship has gone down into the water. What has happened? More volume has come on the forward side. What will it mean? It means that B will shift forward. So, B will shift forward. So, what you have to do is, in this particular case, the ship will keep trimming. In this particular, G is behind, therefore, the ship will trim by aft. So, B will keep moving backward, and it will keep moving till B comes, it coincides with G. So, LCB becomes equal to LCG. When this happens, the ship stops trimming and it is in a stable condition. Okay. So, this is a stable condition when the ship is static. So, you have LCG equal to LCB, that is the center of gravity and the center of flotation acts on the same vertical line. So, this is an important condition for stability for ships. So, this is one condition which, so this is the next condition in the computation of stability. First, we make the weight equal to buoyancy. Number 2, we make LCB equal to LCG. Now, what we have is, we have the final position of the ship. We have the, now the only problem here is probably in finding LCB. You know how to find LCB. There is this center of buoyancy is always found like this. It is the moment of the volume divided by the volume. So, LCB can be taken as integral of AX dx divided by integral of A dx between 0 to L, or between aft perpendicular and the forward perpendicular. X varies from, let us assume that the moments are taken from the aft perpendicular. So, the LCB will be given by integral AX dx moment divided by A dx volume, that will give you the longitudinal center of buoyancy. So, what we do, what is done usually in the shipyards in practice is that LCG is calculated. First, it is fixed. You have the first step, of course, is to calculate the weight distribution. That means, you have to find how the weight is distributed over the entire length of the ship. So, you need to find, there are some methods. For instance, there is a Prohaska's method for that will give you the distribution of hull weight. So, if you like, once you have that, you first find the distribution of weight. First, you find the distribution of hull weight, then you find the distribution of, you add the light weight to it, and you find the distribution of, you have to find the distribution of dead weights on the ship. That is a painstaking process, but it has to be done. The entire distribution of weights is found, and the result, that is your final LCG, is to be found. So, your final LCG is found like that, and so that is the first process. You calculate the total weight of the ship. You calculate the, what we call as a weight curve is to be drawn, where you find the weight of the ship at different points of the on the ship. Start from the aft perpendicular, you go till the forward perpendicular. What is the total weight of the ship? Weight distribution of the ship. What is the weight? So, that is the first step. Next step is to find. Then you need to find the LCB. Okay, you need to find the LCB. LCB is found by integrating this formula. So, using this formula we calculate the LCB, and the there is no other way other than a trial and error process to calculate, make sure that LCB equals LCG. Means if you keep changing the trim, for instance like this. So, if you have the, so if this is the ship and if this is the initial water line, then suppose it keeps, what we do is suppose it trims by some angle. Now, note that at each point you will have the different drafts. This is the important point, that is the draft of the ship is not the same at when the in this case when it is horizontal, the draft of the ship is uniform throughout the, from aft perpendicular to the forward perpendicular, the draft of the ship is the same. But if you have a trimmed line, you will see that the aft of the ship is different, the draft of the ship at the aft is different from the draft of the ship at the forward. We have already done that, draft aft, draft forward, we are finding from the change in trim, we have done those mathematical equations, how you got that. So, this gives you the draft. So, once you find, so you have to find the sectional area at each particular draft. So, at each station you will have a different draft. So, at those each station you have the different drafts, you have to find the sectional areas and integrate it to get the LCB, and you will have to keep varying the LCB, that is equivalent to trimming the vessel. You have to keep trimming it till LCB equals LCG. So, that will give you the balanced condition. So, that will give you the final stable condition of the ship. So, this is to be done in practice in the, that is the first step. Now, remember I have mentioned to you what I have said, I have told you that this is a method that is used to calculate the, this is the stability analysis that is used in the case of a still water, means you have a mean water level or a constant water level and not a varying water level. Now, in real practice you are hardly going to have any still water level, you will never have a still water, you will always have a wavy surface, we have already said that. So, what we do is, just as we described in the last class, we have a way, we first we take this, let us assume that this is the still level. Now, you can take this to be your z equal to 0, okay, you take this to be your z equal to 0, that is the center of the circle. You assume that the circle, the center moves like this, and this, therefore, it traces out a path like this. The wave becomes in this form, you have a wave. Okay. So, you end up with a sagging wave in this case. Of course, it depends upon the type of problem you are encountering, whether you are doing a sagging wave or a hogging wave, that is entirely up to the ship designer to decide which wave he should choose. Now, once you have this wave, we need to calculate the same, we need to do the same thing for this particular wave. It's, this is the purpose, and this is what is usually done in the case of a ship, in a shipyard in case of longitudinal stability analysis. So, you have here the so this is a wave profile, we have already, I have already discussed and described in detail in the last class how you calculate the wave profile, means by the wave profile I mean how you calculate the x and z distance or this z at each station. So, these are each station, we are talking about each station, if these are the different stations, how you, this is the z, this z from each, this z at each of these, of course, z is usually the distance from the z equal to 0. So, this distance, so what, so this distance from this mean level. So, what is that distance we have to know, that we have already discussed how to calculate the trochoidal waves z coordinate. Now, so once you have this z, this problem that we, what did we do, first we made weight equals to buoyancy and LCG equal to LCB. So, we have calculated, we have done these two methods. Now, the same thing has to be done in the presence of a wave, that is the problem here. So, what changes, really nothing much change, no, the problem becomes of course much more complicated, but and the only difference is, see, W does not change, it is the weight distribution on the ship, it is the total displacement of the ship and it is the, I mean W is the total weight of the ship, and LCG you can get if you know the weight distribution of the ship. It has nothing to do with the presence of wave or the absence of wave. Whether the wave is there or not, the LCG on the ship will be the same. So, LCG depends upon the weight distribution on the ship. So, let us fix that is fixed. So, we are not going to change anything to do with the weight distribution of the ship. So, that is LCG and W fixed. The thing that changes because of the presence of the wave is the center of buoyancy, that is it will change, the center of buoyancy will change, the that is the position of the center of buoyancy will change, the buoyancy force will change, and therefore, the LCB and the buoyancy force changes as a result of the wave. Why? Because of the presence of the wave. Remember, if you have the ship like this, if this is an even keel, even water line, that is a horizontal water line, the portion beneath that water line is what we call as the underwater volume. Now, our water line becomes like this. Now, what is our underwater volume? Our underwater volume goes like this, below this, like this. So, this produces our underwater volume. Therefore, we need to find the underwater volume associated with this profile. So, but remember, we have this distance. So, this distance we have as z. So, we have to calculate this distance at each point. This gives you the draft. This gives you the draft at each point. So, like this draft. So, as you can see now, draft is a function of x. If you call this to be the x direction, the draft is a function of x, like this is a trochoidal wave. You have the value of drafts at different points. So, the problem now comes to finding the sectional area. You have to take up your Bongin curves again. You have to find the sectional area for these drafts at each station. You have to find the sectional area. Remember, sectional area is given for each station differently. Sectional area is not the same all over the length of the ship. If it were true, then the ship will be like a box. So, if it is an exact box, of course, only if it is a rectangular box or a square box or a triangular box which is exactly same throughout the length of the ship, you will have the sectional area same. So, since the ship is in a blunt shape in the aft part of the ship, whereas it goes into a streamlined shape in a streamlined design in the front of the ship, that is in the forward portion of the ship is highly streamlined, whereas the aft portion is highly blunt, and the ship shape is not at all symmetrical between the aft and forward, and it changes throughout the station. So, the sectional area keeps changing throughout. So, what you mean by a Bongin curve is a Bongin curve for each station. You will have a series of Bongin curves for each station. So, this is a curve between the draft and the sectional area at each station. So, therefore, you calculate the once you have this sectional areas, you calculate the volume at total volume. Again same concept, but the thing is that A is again the sectional area at each draft into dx. So, this will again give you the problem just comes to finding the. So, A, what we have as the sectional area is again a function of draft, which itself is a function of x. Okay. So, the area is a function of the draft at each point, which itself is a function of x as it varies, and therefore, you calculate this A, you calculate the total volume of the ship. Therefore, rho in, so the first method comes to finding that rho into V, that is the volume, underwater volume, becomes the weight of the ship. That is the first step. Again, we balance the weight, that means the ship is balanced according to Archimedes principle, it is true. So, that is fixed. Then number 2, we are saying that there is no external moment acting on the ship. You should have the LCB and LCG balanced. Remember, the presence or absence of a wave does not really change the position of LCG, the center of gravity, which is exclusively dependent upon the distribution of weights on the ship. It does not depend upon the underwater volume, or it does not depend upon the area or section. It does not depend upon anything except for the location of weights, and that is an external thing. It has nothing to do with water line. So, LCG is fixed, and now the same way we keep varying the LCB. So, we keep trimming the ship. So, we keep trimming the ship until again the ship trims, but it's a slightly complicated process here, because the ship keeps trimming. As it keeps trimming, the shape of the wave will always of course be like this. So, if you have the ship, so you have the, let us suppose that this was some still water line. So, this is now your one water line. Okay, this becomes on water line, and therefore, when the ship trims, about some value like this, if it trims, the water line is like this. So, the draft here changes to this much, draft here is this much, draft here is this much, here, 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 here. So, you see how the variation in draft occurs. You cannot draw it simply. So, that in the presence of trim, the shape becomes quite complicated. So, that will give, but all you need to know is the draft at each point, whether the draft at each station. So, at each station you find the draft, that will give you the sectional area. That will then you, once you know the draft, you look up the Bongian curve section for that station. What is the sectional area? Sum of the sectional areas always to get the total volume of the ship underwater. That will then, and you need to find the LCB, which is the moment of the volume divided by the volume. So, you get the that will give you the total LCB, and you have to keep trimming the ship again until you find that the LCB equals LCG. So, this is one of the stability analysis kind of stability analysis method that is done in shipyards to find out the final position of the ship, that is to find out whether what is the final trim of the ship and what is the final draft of the ship, or this will give you where the ship finally floats. So, this is the condition in which the ship floats, whether the condition is stable, and you can, if you want, you can choose a very rough wave, you can means very strong wave, and you can study what is the maximum amount to which the ship will sink or it will trim as a result of the presence of waves. Now, the next series of work that needs to be done, okay, one thing you should know in this is that, remember, finally the shape of the water plane area, the shape of the water plane becomes extremely complicated. It is not at all a simple area. Remember, in the initial case, when you had a still water, when you had a horizontally straight line, the water plane area is just like the shape of the ship, but now it is a very complicated thing. It is because the water plane area is like this, it is going like this. So, the problem is really in finding the centroid of that water plane area, but since we are only interested in the x coordinate of the centroid, it does not depend upon the z coordinate of the centroid. It is not that difficult, but you need to find the LCF, the longitudinal center of flotation, and the ship always trims about that longitudinal center of flotation, because if you do not know that, then there is no way you can calculate the draft at each point, at each station. The draft at the longitudinal center of flotation is what? It is equal to 0. The ship has no draft at the, or it is equal to some value, the draft is there, means the longitudinal center of flotation is at the longitudinal center of flotation is at the water line. So, it is always on the water line. So, there is some region below that, that is the draft. Now, you need to, now that water line goes like this, the draft keeps changing as you go away from the longitudinal center of flotation. So, this is how we calculate the this is how we do some stability analysis related to the waves. Now, once you do this, the main purpose of this wave analysis, once you find the initial position, is to find what we call as the shear force and bending moment diagrams. That is something we need to do a little bit in detail, which we will do in probably in the coming few lectures. We will, when we are wrapping up finally, we will do the shear force diagram. We will explain what we really mean by shear force, what we mean by a bending moment. We will draw different kinds of shear force, bending moment. These diagrams, we are talking about the, for example, shear force diagrams. We are talking about diagrams that along the length of the ship. So, you draw shear force diagrams over the length of the ship. We will explain what it is, what is the shear force diagram. You draw the bending moment diagrams. So, you draw the bending moment diagrams. So, we will explain how bending moment reaches a maximum at some point, why shear force becomes 0 there. So, a couple of points are there which we will discuss in later classes. So, this is the important thing, you draw the shear force diagram, bending moment diagram, and so you end up seeing where bending moment diagram, these are the points where the ship will experience the maximum, means maximum bending. When the bending moment is maximum, that is the region where the ship will experience maximum bending. So, it usually happens, you can imagine itself the ship will experience maximum bending at the middle, the center of the ship. So, that is something. So, before we go into that, we need to do a little more about waves. So, we will start with that. So, in general we talk about different kinds of, so we have already seen what is a trochoidal wave, and so we are going to assume now all our, whenever we talk about waves, we are talking about trochoidal waves. So, these are the waves that are affecting the ship. Now, there are different ways in which the wave can come and hit a ship. We talk about different directions in which the wave can come. For instance, the wave can come at 0 degrees. I mean 0 degrees means if the ship, let us assume that this is a ship, 0 degrees means the wave is coming like this. Okay, the ship, it is coming in the direction of motion of the ship. Ship is moving like this, ship is moving in this direction, the wave is coming in this direction, same. So, 0 degree angle the wave is coming, we call that as a following wave. So, we say that such a kind of wave is a following wave. If the wave on the other hand comes at 180 degrees, means the wave comes directly opposite to the ship, it comes and hits in the front, we call that as a head wave. So, the wave is coming from the front. Another possibility is when the wave is coming and hitting from one side like this, it comes from one side and transversely it hits like this. So, this like this. So, the wave comes and hits like this. So, the wave crest, this line is actually perpendicular to the line of length of the ship, the line joining the wave crest, this line is perpendicular, that is called as a beam wave. So, we talk about different types of waves and their effects on the ship. Then now, there are important effects of the ship on the effect of waves on ship stability. So, now okay. Now, suppose you have a ship here, now as we have seen, there are a couple of possibilities of producing the ship. Let us talk about what we called as a sagging wave. In this case, first let us start with, we will start with a sagging wave. Okay. Now, remember the ship, first remember that the shape of the ship is like this, that is the center of the ship is mostly wall sided. If you remember what we mean by wall sided, it means that the breadth of the ship hardly changes as you go up, it is like this, it is in the centroid, in the center, it is the thickest region. And if you remember if you have seen some of the line span drawings, if you remember the midship, if you look at the station in the body plan, if you look at the station, you will see that it is like this mostly. It's you are not going to have much of a difference in the breadth of the ship as the draft changes. So, if the draft changes here, if the water line goes up or down here, there is hardly any change in the breadth of the ship. But when you go towards the front of the ship and back of the ship as well, you will see that it goes up like this. In general, everywhere it is like this, that is it goes up in this fashion ship. So, if your draft increases, so if you call this to be your draft, so if your draft decreases first, let us assume that the draft decreases, means initially if the water line is here and then the water line is here, this is WL0 and this is WL1. So, initially your water line is here and then your water line came down to here. Now, in case you have a situation like this, there is a decrease in draft, you see that in general the breadth of the ship has decreased, right. So, the breadth of the ship, this is, what is this? What have I drawn? I have drawn the half ship. So, this is the body plan. What I have drawn here is the body plan. So, body plan is actually, so if you look at it in the body plan, what you are seeing here. So, if you look at the ship in the body plan, that is ship like this, you look from here so you will see that the shape of the ship actually keeps going like this, which means that as the draft keeps increasing, if it keeps going up, if you go away from the keel towards the deck. So, if the draft of the ship keeps increasing, the breadth of the ship continuously keeps increasing. Okay. Now, why do we keep mentioning this relation between draft and breadth? What happens as a result of wave? See, what we are studying here, we have done all the stability analysis as far as a still water line is concerned. There is not much left, there is nothing much left in the still water stability analysis. We are now diverting into the difference in the case of a wave. So, in the case of a wave, the main difference is occurring in the draft at different points, means the water line is no longer straight, therefore, draft is no longer the same as the draft in the case of still water line. Because of the presence of wave, its draft is changed, because some region it is crest, some region it is trough. So, therefore, some region the draft is more, where there is a crest there is a more draft, where there is a trough there is less draft. Therefore, our problem now comes to the effect of draft. So, effect of changes on draft. Now, we have seen as the draft increases in general. So, in this case, in this particular case, let us look at this particular case. What has happened? What do we see here? So, this is a sagging wave over the whole length of the ship. What has happened here? We have seen that initially the water line was only this much. In this region, first let us consider the midship region. In the midship region, what has happened? The draft has decreased. Initially this was the draft, if that was still water line. Because of the presence of wave, the draft has decreased, it is only here. So, this is the draft now, it is no longer this much, this is the draft now, not this, this will be the draft now, this is the water line, therefore, this is the draft now, and initially this was the draft. Now, in the midship part, we have already seen the midship part is, because of the change in draft, there is hardly any change in breadth, because the midship is actually a wall sided, it is almost like this. So, but when you now this is what happens in the midship of the ship. When you go to the front part, when you go to the forward part of the ship, here you have seen that there is you see that here there is an increase in draft. Initially the draft was only this much, D initial, final draft is this, D final. There is a change DI, D for F. So, you get the initial draft and the final drafts. So, the final draft in the forward part is much more than the draft initially, in the absence of a wave. Now, what did we see? If the draft increases, we have seen that the breadth increases. Now, what is the effect of breadth on the stability of a ship? This is the important part, that is how is the breadth of the ship related to the stability of the ship. Now, what is I of the ship? Water plane area, I is always proportional, is LB cube by 12, you have seen. Therefore, I is proportional to B cubed. I is the moment of inertia of the water plane area. So, it is proportional to B cubed, which is the cube of the breadth. Now, here what has happened? The breadth has increased. So, when the breadth has increased, the moment of inertia will increase. Now, what happens as a result of the moment of inertia increase? I increases, Bm given by I by del increases, it increases. Okay. Therefore, Bm increases, metacentric radius increases, m goes further up, GM increases, metacentric height increases. As a result, there is an increase in the ship's stability. So, what we see is that when the ship is on a wave trough, this is what we have done, this is what we mean by a sagging wave. Ship is on a wave trough, stability BM and hence GM increases. Okay. So, the metacentric height BM increases means it is mostly because of course, there is a shift in B down and there is an increase in M up. So, because of that the BM increases and consequently GM increases. Okay. Now, therefore, the stability increases. Therefore, the stability of the ship increases. So, what we see, if the ship is on a trough, remember if the ship is on a trough, the stability of the ship increases as a result of when you compare it with the ship's stability on a still water, the stability of the ship is more in the case when the ship is floating on a trough. Let us consider the other case, the ship is now floating on a crest. What do you mean by ship floating on a crest? That is the case of a hogging wave. So, this is the like this. Now, this is a hogging wave. See the ship, ship is floating on a crest means the center of the ship, there is a midship of the ship is on a crest. So, there is a crest. So, the means like this. This is a wave, ship is here. This means it is not here, the whole ship is here. The midship section is here, it is floating like this on a crest. Okay. So, now what happens? The reverse of what I just said before occurs here. In this case, you see that in the midship again there is a increase in draft again, but that does not change the overall breadth of the ship, it does not change I so much, because in the midship the ship is mostly wall sided, there is hardly any difference in B or the center of there is hardly any difference in the breadth, and consequently the moment of inertia does not change. But here on the front part of the ship and even on the aft side of the ship, what has happened? The draft has decreased. Initially the draft was this much, this was D initial, now the draft is only this much, D final. So, there is a very strong decrease in draft as a result of the ship floating on a wave crest. Okay. D initial and D final, dF is much smaller than D initial. What is the consequence? The breadth of the ship, effective breadth of the ship. Remember, the breadth of the ship is varying over the, so and therefore, the I is no longer a very as straightforward as last time. It is not like LB cube by 12, very straightforward we calculated for a, it is for a box shaped barge. When you have a rectangle, you can do LB cube, but it is proportional to B cube always. The at any point, that means between any two stations, that small strip, it is always equal, it is proportional to B cube, the I, the moment of inertia is proportional to B cube. Now, or the half breadth cubed. Therefore, what we see there is a very strong decrease in, as a result of the ship floating on a wave crest, there is a very strong decrease in draft in the front part of the ship and in the aft part of the ship, as a result of which there is a strong decrease, there is a very sharp decrease in the half breadth at that, in the effective half breadth of the ship. Means there is a change in the breadth, there is a decrease in the breadth of the ship in the forward part, and there is a decrease in the breadth of the ship in the aft part, there is hardly any change in breadth in the middle part. So, effectively there is a decrease in the breadth of the ship, as a result of which there is an effective decrease in B cubed, as a result of which there is an effective decrease in I, consequence of which there is an effective decrease in BM, that is a metacentric radius, and therefore, there is a effective decrease in the stability of the ship. So, the metacentric radius decreases as a result. So, what we see is that Therefore, for a ship floating on a wave crest, therefore, for a ship floating on a wave crest, there is a decrease, effective decrease in BM, consequently in GM. So, M actually comes down. So, there is an effective change in GM, or the metacentric height is effectively reduced, or there is a decrease in stability of the ship. Okay. So, there is a consequent decrease in the stability of the ship, because GM is now much smaller than it was in the previous case. Therefore, when a wave when a wave actually passes through a ship, let us suppose that a ship is moving in this direction, and if a wave comes in a probably a in the head, if there is a head sea, if there is a head wave, if a wave is traveling, if the ship is traveling in head seas or a following seas, and suddenly the ship comes on a wave. So, what will happen? First the ship will go on top of a wave crest, then it will go on top of a wave trough, then it will go on top of wave crest again, and it will keep going up and down. So, the ship will be actually varying in terms of its position. It will be varying in its position as in the wave crest and trough, it will keep varying like this. So, what happens as a result? As a result of this movement, when it is on a wave crest, the GM decreases, when it is on a wave trough, the GM increases. So, the stability decreases, stability increases. So, GM is now becoming a function of time, because of the movement of the ship like this. GM is actually a function of time. So, the stability keeps decreasing much more. So, those calculations which you did using still water line, that is GM using still water line, does not really hold good. In case of a wave, you are seeing that the GM is actually now a function of time. It keeps varying, it decreases much further than its value in still water, then it increases to a value of still water, then it increases to a value above still water. So, stability increases, decreases. So, of course, we are not bothered about what happens when the stability increases than the still water level, it is more stable, it is fine. But there are very particular dangerous situations when the ship is on the wave crest, when you have your GM very small, and it is possible that in many cases the GM can keep decreasing to such a value that GM can even become negative. So, the GM can this GM can end up becoming negative in such cases, and as a result, remember your GZ, which is GM sin phi, also becomes negative. So, righting moment is actually becoming negative, means it is actually a moment that is going. So, if there is a small wind, there is a heeling moment, this righting moment is now opposite to the restoring, it is no longer restoring the ship, it is trying to destabilize the ship, it adds to the wind heeling moment. So, it is most likely that the ship will capsize. So, it is wind heeling moment plus the righting moment, or GZ is negative. So, GZ plus the wind heeling arm, total, that will become the total heeling arm, the totally entirely it is trying to capsize the ship, and therefore, the ship is highly unstable. In this is when the ship is on a wave crest. On a wave trough, of course, the ship is more stable, but since it is a transient phenomenon, it is an unsteady continuous transient phenomena, or it is varying with time, it is a time dependent phenomena. You are bothered about what happens in that case of a unstable case, when it is on a wave crest and its GM is decreased and it is even probably negative. So, this is some of the important concepts dealing with the stability of ships on waves. The concept we will do a little bit of this analysis, and we will continue with this in the next class. Okay, thank you.